Everyone, it's Ezekiel O'Callahan with Raptor Chatter here to talk about my own rock collection. We filmed this a while ago and the framing was a little bit off, so I apologize for that. However, we've also filmed this 3 or 4 times, so we're just going to kind of have to roll with it. I do want to mention with the editing, we did set it up so it would be fossils and then minerals, and that there are timestamps down below in the description so you can jump to different things that you might be more interested in. As well as that, there is a very large rock towards the end that I think is pretty interesting because I got that one myself. You get to hear that story if you watch that long. And, you know, that's pretty much it, so let's get started. So we're going to start out with the most controversial fossil that I have. So this is a skull, probably of an Eohippus, which is a very, very old ancestor to the horse. Belongs in the same family. This is from the Badlands area. We're not exactly sure where because this was privately collected, meaning that someone found it and went, oh, I can sell this, and then they sold it. This was also gifted to me, otherwise I would feel much more conflicted about it. But essentially, since we don't know the exact place it came from, it's hard to get some of the scientific material from it. But my plan is to essentially just use it as a teaching tool and prep out just half of it, and have the other half still encased in the rock like it is on this side, where you can still see where the mud filled in all of the holes. And that way, hopefully at least, that way, it can be a good indicator of how much work goes into the preparation for these kinds of fossils. Because there's a lot of work that goes into these, and the people who do this professionally are very, very good at what they do in prepping out the rock. So this is actually from my grandparents. This one is, I believe, dinosaur bone agate, or agatized dinosaur bone. Since it was kind of in a random box of a lot of rocks they had, I'm not totally positive, but it does show a lot of the, I guess you could call it marbling, but essentially where the veins would have been within the bone, where the marrow would have run, that kind of thing. And so this isn't entirely uncommon to find. You can find like gemstone quality versions of this where it's a little bit nicer, but this one's decent enough, and we're actually probably going to, end up sending this one because it's cut and polished. There's not much scientific value in it. Getting it cut and sending it to a jeweler so we can get some rings made out of it for my wife and I. Alright, so these are both Megalodon teeth. However, you can see one of these is from a much older Megalodon. You can see the nice burlette here, which is this nice dark part coming in. That's one of the more identifying parts of a Megalodon tooth as opposed to a different kind of shark's tooth, because there were still other very large sharks before Megalodon, and so it's part of the way that you're able to tell whether or not it was or was not a Megalodon. We also have this much smaller tooth, much smaller tooth. So this one's from Morocco, Eocene Morocco. There was a sheet I saw that had all the stuff that I think I have saved somewhere, but I haven't looked at it again recently. It's a place where a lot of sharks' teeth are pulled from because they know they can get them relatively easy. This is a ray plate. This is also from the same location as this. This would be much flatter. The rays use them to crush up crustaceans, crabs, that kind of thing. And then we have this odd tooth here, which I'm not sure what this one is. It may actually end up being a dinosaur, part of a dinosaur tooth, probably like a Carcharodontosaurus or something. But it was also in this, which doesn't mean that it lived past that time. Essentially, it would have been in an older rock and eroded out of that rock. And since it's still the enamel, which is very hard, it would have survived transport into where all of these teeth were being deposited. All of these kind of teeth were being deposited. And then also been buried. I'm not well enough versed on dinosaur teeth to be able to identify for sure that's what it is, but one of the other people who has looked at a lot of those teeth has found Carcharodontosaur teeth out of that deposit, so it wouldn't be wildly unlikely. So this one's in a stand. Let me get him and I'll pull it out. Okay, so this is the back side. Let's see if you can see one. So right there's a little crinoid, and right there's a little crinoid. But if you flip it over, you can get a lot more crinoids because it's just much clearer. We also get this long line, and it's actually spiraling if you look at it. My wife's family got this from like one of the storage lockers, kind of like Storage Wars. My wife had thought it was a spine of something because you have like these nice kind of crosses going across the long central column. But it actually isn't. This is a fenestrated bryozoan of the genus Archimedes. And so Archimedes was a Greek scientist, essentially, who had this idea for Archimedes Screw, which was essentially the same idea here as far as shape is concerned, where it's this long spiral that comes up. And so there would have actually been large flat nets kind of coming off of these, where the animal would filter feed from. So these were only around for a very short time, I believe in the Carboniferous. And so it's really cool to be able to actually get one. I was going to try and spend some time this summer trying to find one, but then one just kind of fell into my hands, so that was convenient for me. This is from New Mexico, and this is really nice because you can see both sides of it, essentially. This is from the Pennsylvanian, and the group who essentially has the quarry does try and prioritize selling their fossils to museums and for research purposes rather than just for profit. This is something that's relatively small, and so it's okay for it to be privately owned. It's not necessarily preserved well enough to be easily identifiable, but there are both sides here, so it is something that is cool for me, at least. I like having both sides of it. Petrified Wood. So this is technically also quartz. It's closer to a jasper than anything because essentially the minerals inside of the wood would have been replaced by quartz over time. This is from near the petrified forest, not within the park, but there are a few places you can collect outside of the park. And so you're able to get little pieces like this. You can see the nice kind of conchoidal, like curving fracture there that you get with it. Yeah, this is a very nice one. Do be careful with some of these. Sometimes you can find little trace amounts of uranium in it, which generally you're going to be fine. But if you're set it on your nightstand or something and you're standing next to it all day or sleeping next to it all night, it may not be the best. These are other pieces of petrified wood. This is from the Blue Forest, I want to say in Wyoming, Montana, somewhere back north. But different kind of minerals going through the quartz that essentially would have gone through the trees and replaced it. And so you get different kinds of coloration in it. But you can still see some of the wood grains through it. You can look at the sides and you still see some of like the radiant pattern of the rings going out. This one is really interesting. This one is from near petrified forest as well. These are not necessarily knots in the trees. These are more like bacterial growths that then mineralized as well. So that's where you get a lot of these different kinds of things. But you can also see the very radiant patterns here, a little bit of the kind of bark on the outside, and you also get to see the difference between not polished and nicely polished. I personally like the not polished side because it's more of what you would expect it to look like when it came out of the ground. Alright, so now we're going to do ammonites and nautiloids. So this would be a nautiloid. This is, I want to say, from the Ordovician. A lot of times this is sold as Orthoceras, but it's not an Orthoceras. Orthoceras was much larger and wasn't found in this area. These are mostly from Morocco. And then you have this long line within it, which all of the other ammonites I'm about to show you that are still coiled have. They're just also coiled, and a lot of times they're inside so you can't really see them. But essentially, this is used for gashing. It's called the siphuncle. So that's how the animal would have stayed buoyant in the water column, is it would exchange gases within the individual chambers and with the water column. But eventually, these started to become more curved. I don't remember which variety this is, but for our purposes, we are going to treat this as if it did not have sutures. So essentially, you get these nice straight curves in sutures in the very early ammonites. And so that's something that's very characteristic, but as you get further along in time, they start to get more complicated, where you get things like this. And so this is from Jurassic, and you can see again that this is a little bit wild as far as it getting more and more complex. And there's not really any real guesses as to why they were doing this. It may have been just predation avoidance or something. Some people have suggested that it was so that they could deal with deeper pressures in the bottom of the ocean, but even modern nautiloids go to the bottom of the ocean and they do not have this kind of suture texture. They just generally have these much straighter chamber separations. You can see kind of here where it starts out straight, gets slightly more complex, and then this one is actually a good example of both of what I was going to talk about. We're going to start just with this up front part where you have these absolutely wild sutures, even more complex than just the little lines here. These ones are all intermingled, so this would have been a Cretaceous one. But you can also see on the outside of calcite where it is hard to tell unless you start getting into the shell itself. And even these internal septae that are separating out the chambers really don't see a ton. This one is agatized, and so you do have like a little quartz geode inside of the animal, which is pretty neat. And of course you have things like this. This is from the early Jurassic. This is like, I want to say Yorkshire. Where you have an ammonite that was essentially split open, have a little bit of it on the edge, and you can see both sides of it. You can't really see any of the internal structure, so it's really hard to say, for me at least, off the top of my head, what more this would be. I'm not an ammonite expert, so when you find Crynoids, it's something more like this, where it's just a few columns. And so essentially this would be the stalk of an animal that would have a large head, essentially a calyx, that is filter feeding the water. And that calyx would look something along the lines of this. Obviously these are much different sizes. That does not mean that this animal was so much larger than this one. at least as far as the calyx is concerned. This one may have just been living in a much more dynamic environment, a lot faster running water, that kind of thing. And so it may have just needed a more sturdy stem in order to succeed. Whereas this one would have been much more steady water. Essentially, so you would come up to the bottom of this, you'd have different arm sections, essentially. Reach out into the water and filter feed. Now, this one is probably a composite where they essentially found the nice part of the pieces, but it was very fragmentary because the back of this is much more concrete. But that's something that they do with a lot of the different fossils, essentially, is that they will mount them onto something else. This one was relatively cheap for how much most of these go for. I obviously was okay with it because I wanted a decent Crynoid, and this is a decent Crynoid. So Trilobites took all kinds of different forms. These are actually both from Morocco. One I got myself and one was gifted to me. They're calamine or flexicalamine trilobites. I want to say Phaeopsids, but I'm not sure. So essentially, trilobites have three parts of the body, where you have essentially this central part and then the two parts on the side, but at the head you have essentially the three parts there, three parts of the head, three, lobe, head. This is another Phaeopsid. You can see some good details here. This one's from Utah. You can see where they've actually prepped out with an etching tool, essentially where it is. I want to see if you can actually get any of the details on the eyes on this one. Yeah, like up here on this part of the eye, you can actually see some of this schizochrol eye, which essentially just means there's little calcite lenses that are separated by essentially thicker parts of calcite. And so that means those eyes do preserve very well because they are that calcite. They can be replaced by other minerals, or they can just stay preserved very well. Which means we actually have a very good understanding of how trilobite eyes work, just because they're preserved so well. This would be another animal that's related, again, calamine or flexicalamine. I'm not a trilobite guy right off the top of my head, so I can't really say for sure, I'm sorry. This one actually is interesting because you either have little parts of the crystallized calcite in there, or you might have what's called pyrite disease. Sometimes pyrite will just grow on fossils, and it can do a ton of damage. Going into other types of trilobites, I have a Bentonolithus chamberlaini, 480 million years old. This is an Ordovician one. You can see these large genial spines, which are essentially the spines coming off the side of their heads. This one had those spines that are longer than the rest of its body. Some of these get absolutely ridiculous in some species, but it is still very interesting to have these kinds of things. Trilobites are relatively well studied, so there's not too much concern collecting a lot of them. Be careful with some of them depending on where they're coming from, but like if you're collecting relatively cheap specimens like these, you're fine. They're well known, they're well studied, they're well cataloged, and also people do make fakes of them sometimes. These are real, and I can essentially point out why. One, this was a reputable dealer and was coming from Wales, not necessarily a place known for fakes. And then the damage on it is something you would expect of real fossil. Not to say just because it's damaged it's real, and if it's perfect it's not. I'll get there in a moment. This one you can see the cracks going through it. That is another good clue. This one, the kind of very fine detail isn't normally found in a lot of resin casts, because the resin is just like, okay, pour it in, cool, we got something that looks like it, great. So if you have that kind of detail, you're probably doing pretty well. A lot of times they will glow funky colors in UV as well if they're not real. And none of these really do. You just essentially see one part that's slightly lit up more because it would be made out of resin or something. So when I was talking about the Crynoids, I was talking about five-way symmetry, which is also had by Starfish. This one's from Russia. I don't remember the exact place, but I have it written down somewhere. And so, again, Starfish, five-way symmetry. They're both echinoderms. This one is actually really interesting. This one's from the Middle Jurassic of Germany. It's from part of the same formation that Archaeopteryx is from. But you see this very fine preservation. Normally you don't get these preserved. And what essentially happened is you would have lagoons. You'd have your shore face, and you'd have a lagoon here. And the evaporation in the lagoon would be happening faster than water could fill back in. Meaning that you would get a lot more salt in that water, and it would concentrate even lower. It would be more salty at the bottom. And that salt essentially stops scavengers from destroying whatever dies down there, which is part of how Archaeopteryx got preserved so well. And especially since it's a lagoon, it's very still water, so you're not going to get as much of that kind of topsy-turvy, wavy bit that's going to damage the fossil as well. So that's part of how we were able to get such fine fossils coming from that part of Germany in what was the first discovered Lagerstätten the Solnhofen limestone. And then here we have two different varieties of essentially the same fossil. This is essentially also life position. This one is a cut slab. It's been more mineralized, whereas this is more just sand. These are both stromatolites, and so you can get these nice bands because essentially it's a bacterial colony that grows out over itself. Tide comes in and covers it in sand. A new bacterial colony grows on top of that, and so you get these nice bands in it. This one's been mineralized. It's also probably been metamorphosed, part of why you get so many different bends and whatnot in this one, which makes it hard to identify. But if you look at the top of these ones, you can see the nice concentric circles, as these would have essentially just grown next to and on top of each other. Kind of the oldest parts of life on Earth that are known. There's another kind of rock that does help show this, but these were the first photosynthesizers, at least. I mean, they produced essentially all of the oxygen in the atmosphere. Before that, there really wasn't that much oxygen, and not that much oxygen in the water as well, meaning that they were a major part of how life got its start. Okay, this is a leg bone of Coryphodon. It's an Eocene mammal, medium-sized, probably kind of hippo-like. Showed up after the extinction that killed the dinosaurs. If you look on the inside, you can see where the marrow would have been in the vessels. It's essentially just a fragmentary leg bone, so it's not terribly tragic for it not to be in a museum. But yeah, just like a nice little kind of a shelf piece of a little mammal bone. Alright, so one of my favorite groups that is now extinct, unfortunately, is the sea scorpions or Eurypterids. Here's a Eurypterid. Let me actually... Alright, so I let this one down so you can actually hopefully see it a little better. But Eurypterids. You have this essentially would have been a swimming paddle, and it would have swam kind of like a penguin, where it would have oriented those up and down and kind of wiggled through the water. But it actually would have worked quite well. These were predators, just 100% predators, likely fed on early vertebrates. This one is Silurian in age, so it probably would have been around about 420 million years ago. You're getting some of the little front legs coming out of the sides here. If you look really closely, actually, a little bit there, but then also right here, that would have essentially been the eye. Just two little slits there on top. Not slits, but kidney beans there on top. This kind would have been swimming around, and if this piece hadn't broken off, it would have come to a full point, which is why they've been often called sea scorpions. Although they aren't scorpions, they are related. They aren't quite arachnids, they are chelicerates, which just means they have certain specialized mouth parts. But these are probably more closely related to things like the horseshoe crabs. So earlier you talked about slabs and counterslabs. This is a small fish coming from Morocco, but my brother actually has the other slab of this. And this is just a fun thing that we both have one of these. Fish get fossilized a lot more than other animals, at least vertebrates, because they're where essentially rocks are being buried. Because you need to be able to bury an animal in order for it to fossilize. And where a rock's being buried, where there's deposition, where's deposition happening, where there's water, where are fish, where there's water. So you get a lot more fish than animals that live on land, as far as vertebrates are concerned, for fossils. Now we're out into stuff that I've collected. So this is pretty much all from the Naco Formation of northern Arizona. This is from near Pine. There's rugose corals, which I'm actually going to pull one out here so I can show you a little better what they are. So essentially, coral today are a bunch of colonial polyps, but back in the Paleozoic, there was this group called rugosa, which essentially made their own polyps larger and didn't worry about the colonies as much. They still had some colonial forms. But you can see the different septae there, essentially where it's split up. And this is essentially, it would have sat on the bottom of the ocean and had little fronds coming from this and fed on what was drifting by. And I have a few of those. These are probably all the same species, to be fair. This is essentially a mash from the Coles Ranch locality of the Naco Formation. And that's because there's just, it's pretty much all fossils. Some people might consider it a coquine, although I think there is still some mud in here. It's not quite all fossils. You have some like Crynoids, some there that have actually busted open, so you can start seeing the little shape of the individual columnals. Different spines, which I'll talk about later, because I think I have one that's more visible there. Brachiopods in here? Yeah, I have a little Anthracospirifer in here, which is a little small thing. They look a lot like clams, but they have a different symmetry. Brachiopods are going to essentially have more like this, where they'll have a symmetry from right to left, more or less, but the shells do not match up. And so that's something that you're going to see here in a minute when I pull up what is essentially a collection of a bunch of the different fossils that are from there. And this is most of the stuff that comes out of there regularly, although not quite all of it, I will admit. So these are a couple different brachiopods that are from the area. I want to say that one's a Derbia, but I don't actually think it is. But that's an Anthracosphere for when you can see a lot better. This is a Composita, which is another type of brachiopods. These are all brachiopods. This is a type of Productid, and the little nubs you see on it would have essentially been longer spines. And people think it was probably buried into the mud for the most part and would have fed that way. This one here, you can actually see some of the internal features of it, because sometimes the lophophores, which are essentially the filter feeding tissues, can actually mineralize as well in brachiopods, which is really cool that you're able to see the same essentially feeding structures from brachiopods that were around 320 million years ago versus today. This one is a gastropod, little snail. They're not super common from that area, but it's really cool. This is the Bryozoan that I was talking about. This one isn't an Archimedes Bryozoan, but it is also a fenestrate Bryozoan. So it's related, but not quite the same. This one would have essentially just formed large sheets on the seafloor, but got some good shape and texture there. This is another crinoid columnal. So this is essentially what it would have had for its column. This is another bryozoan. This would essentially be a branching bryozoan. So essentially there's these kinds of bryozoans that form big sheets. There's these kinds of bryozoans which kind of branch out everywhere, which another person found a really nice one of those. And then there's these encrusting bryozoans down here. So this is a composita, like I mentioned, but if you look really closely, you can see this little texture kind of netting on it, which is essentially the bryozoans would have landed on top of this and then spread and grow across it. And that growth across it is essentially the colony. So those are called epibionts when you find an animal living on another animal. So even like barnacles living on whales, epibiont. And finally, we have this little spine here, which is also from a crinoid. That is essentially a spine for the anal tube. And so essentially the snails would sit on top of the crinoid and eat both the waste from the animal, but also steal some of the nutrients that it was filter feeding in. And so these spines were essentially meant to keep those snails away. And that one just fell. Damn, I'm gonna have to get this reset when I'm done. This is actually a whalebone. These are probably some epibionts and barnacles and stuff that formed on the rock before it got buried fully, or on the ear before it got fully buried. And spoilers, this is the ear of a whale. It has a very unique shape, and this is actually kind of the shape that they found in one of the early whales that made them go, oh, that's a whale. Because the animal they were looking at was much more wolf-like, and while they were prepping it, they accidentally cracked open part of the skull and went, oh no, we cracked open part of the skull. Oh hey, that ear is really weird. And they found out it was a whale that way. And so this is just another example of how very specific parts of anatomy can be used to identify different relationships between different animals. So this is a mammoth bone. This is leg bone. This one was also gifted to me, but this one did have time to be studied. This one was from one of the universities in Alaska, and they essentially sold it off because they needed to make more space for stuff that wasn't falling apart, which, as you can see here, by this giant seam of glue, this one is falling apart pretty well. This is also the oldest record of the mammoth from Alaska, so that's probably part of the reason it's falling apart so badly. It's just really cool, and like, it's nice to be able to have pieces like this that did get studied, but also don't have as much use anymore, and be able to use them specifically for that. Because there is still research going on mammoths, but not necessarily this bone because it is so damaged. So these are both fluorite, and obviously they're very different colored, but they're also differently shaped. And there's a reason for that. So this one is essentially the method it grows in, and this is from a mine in China. You can see it grows this very naturally cubic shape. That is how it shows up when it is found in a really nice specimen, at least in the wild. It grows like that normally. If you break it though, it breaks along essentially these planes, which is called the cleavage of the mineral. And so it will break just along these general planes. You can do it in a lot of different ways. Diamond actually breaks like this as well. So when you see cut diamonds for rings and whatnot, they're actually cleaved kind of like this, except with more advanced techniques in order to get the shape that they want, rather than cutting it, because diamond's very hard. It's hard to cut. This is a really nice specimen though. It's so clear. It's so beautiful. Let me see if I actually have my... This one doesn't show it too much, but you can at least see a little bit of where it fluoresces. But fluorite is so called because it fluoresces, or actually I think fluorescence is so called because fluorite shines. Alright, and so this is Lapis Lazuli. This is a metamorphic rock that has a couple different minerals in it. So you can see there's some pyrite in there, the little shiny bits. The blue is lapis. That's the name of the rock. And then the white bands are going to be calcite, which comes in many different forms from many different places. Metamorphic, you can see where it makes these very distinctive bands. And that's essentially because the whole rock was getting pressed from these angles. Any minerals are going to normally essentially push to line up with that pressure. As for the pyrite in that rock, there's another piece of pyrite. This one's from Spain. When it has the space to grow, it will grow naturally this cubic shape, a lot like the fluorite. Not all minerals grow cubic shape. I have other ones that grow in different shapes that I'll be getting to. Yeah, but like you said, this is just a nice piece of pyrite. And then we're going to be looking at quartz and tourmaline. So this one's tourmaline. This is a large piece of tourmaline schorl, which is just a variety of tourmaline. There's a lot of different varieties of it. Black, very fibrous kind of look to it. One of my favorite minerals. And then as you can see on each end, it's just busted off. It doesn't cleave in any particular way. Quartz is the same way. It doesn't really cleave. You can see on this piece of quartz with tourmaline, tourmalated quartz, where essentially both of them just, when they broke the piece off, it just snapped there. But it did start growing some of the crystal shape. Another piece of tourmalated quartz. This one is more black than that slightly lighter version, and the quartz isn't quite as nice. It's a lot more murky. And then you have these tourmaline crystals in there as well that are a lot darker as well. And finally, you have one of my favorites. This is a more fancy type of tourmaline, and as I was mentioning, there's a lot of different varieties. This one we're not really sure what it is, and the reason for that is there's a lot of tourmalines that look very similar to this, and the tests that you would do in order to find out which tourmaline it is are normally more expensive than the tourmaline itself, because you're looking for very small, minute changes in the elements that make up the crystalline structure. Tourmaline is really unique in that it has a very large chemical formula, and a lot of different elements essentially fill different spots within that formula. So it's a very complex element. And still in quartz, we have grape agate, which is chalcedony. It's essentially dissolved quartz in probably a basic solution. But you can also get it under certain pressures and whatnot. It would have precipitated out into these nice little round balls. It has a little bit of druze on it on the top, where essentially you'd get a nice point like this, a little six-sided point, except they're all very, very small and covering this thing. So that's the idea behind druze. Alright, and then we have, this is aquamarine, like you might see in a gemstone. This one isn't quite the same quality, but it is fairly clear still. Again, slightly fibrous texture. Up towards the top, it's a little more structured, and you have a nice flat top. That's all probably polished. Although when they do end, sometimes they do end on a fairly flat top. Also, you can see where they broke it and it didn't cut it because it's just broken. Another one of the minerals that doesn't cleave quite like the fluorite I showed earlier does. Slightly blue. You can get them that are more blue, and those are more desirable, but this is a reasonably large piece that's reasonably clear, so it was good for my collection at least. So this is halite. Halite is more normally known as NaCl, table salt. However, obviously this isn't quite something you would put straight on the table, but you can, give it a little like salty. Very crystalline, square crystalline shape. It also grows that kind of shape. I really do have other things that don't grow in that kind of shape, because you don't always get minerals growing in perfect crystalline shape. But yeah, essentially it's a evaporite mineral, so you would have had a dry lake or a lake bed that was drying up, and the salt would have just not evaporated with the rest of the lake. So that's essentially what halite is, where it comes from. Not too uncommon, but it is neat to see. Okay, so this one's from Tanzania. This is ruby and zoisite, so the red part is the ruby. So if I get it damp a little bit, you might actually be able to see it a little bit better. So the zoisite is the green, you can see the green on the other side as well. And then the red is the ruby. This one actually fluoresces a little bit. There are other wavelengths of UV that will actually make it fluoresce a little bit more, but you can at least see a little bit of that red glow in there. And so that's just really interesting. It's just certain minerals respond to UV light to give off even brighter colors in a lower light frequency. Malachite, a copper mineral. This one is botryoidal, meaning it essentially was squeezed out of something almost. Like the liquid was getting squeezed out as it was very high in the mineral, so it almost, once it got that space, it essentially would have let go of that mineral as quickly as it could. And so you get these nice little patterns up on top of it. Don't breathe in the dust from this one. This one actually is toxic, so you don't want to necessarily go around grinding it up too much if you can avoid it. But again, it's only if the dust is in the air, so handling it like this isn't too bad. And this is another quartz replacement. This one is a gastropod though. Essentially you would have had a snail or something that died. The shell, which is made out of calcite, would have dissolved away because calcite dissolves in the face of acid. And then the quartz would have come in and essentially replace all that. And that does give you a little bit of the druze. Like I was talking about, this is a slightly larger druze. So yeah, this is something that can happen. This one's from India. I don't really know much more about it other than that. But it is just a really neat little teeny tiny fossil. And it does show how interestingly quartz can be a way for a lot of fossils to be preserved. Okay, on the subject of calcite, we have this one here. There's a couple different features about these. One, this one has a much more unique crystal shape. You can see it has a lot of this kind of jaggedy bit, but the cleavage planes are essentially these planes where it's just kind of pushed over box. And this is not the most uncommon kind of shape in the world for a lot of rocks. Calcite comes in a lot of varieties. As you can see, a lot of colors too. You can't just define a calcite based only on its color. They come in every color. But they do normally will have this kind of shape when you break them. They have this kind of cleavage, although sometimes you can get entire crystals that are so small that they won't necessarily break perfectly along these lines. Like this would have been one much larger crystal that they then broke down into this nice clean piece. Or you can get things like this where you don't necessarily want to break it. But it does react to acid. A little bit of acid in it and it'll bubble up a little bit. One of the cool features about it as well is if you have a nice clear piece. But if I make just a single line here, I put the calcite over it, it has double refraction, meaning that it essentially, the light reflects it both back in from different directions. So you get visual of two separate lines being there despite there only being one line. So you get this, it's just a really cool feature of it. But makes up a lot of animal shells, not necessarily in this form, but something that you do see a lot. These are some of the minerals that have different crystal shapes than just growing in square. This is lepidolite. It is a type of mica, and it grows into fairly amorphous crystals, except for they often have these kind of flat parts where the cleavage planes are. So I was talking about the cleavage planes on the fluorite, essentially making that double-sided pyramid. These ones are essentially just flat planes where you have one here, and that's essentially where it will break. It will break into these nice flat, very flat sheets, and they're actually pretty malleable. What I can do is I can kind of fold this piece back. That is technically part of the rock. You actually have some quartz and some feldspar in on here too. You can get other smaller pieces of mica if you go look at gravel in someone's yard. If it is granite, you will probably find some mica in there, little black flecks kind of thing, not necessarily purple. But to get something that's this large, it does take a lot slower of a cooling time. And that's actually how you get a lot of these minerals that are from volcanic or magmatic sources, is you need a much longer cooling time. This one is garnet. This is actually most likely from a schist, meaning it would have been a metamorphic mineral. But the elements inside of that rock, rather than what I was talking about where it lines up flat, essentially would have grown this little, essentially nugget of a separate mineral that didn't really have any of those kind of flat symmetries. So it would have just sat within a layer of mica and whatnot. This is azurite, another copper mineral, very soft, you want to be careful with it. But if you look at closer, there's a little bit of the druze. When I first got this, there's a lot more of it, but you can see a lot of those crystals on the outside have worn away because the rock is so soft. It is a very beautiful blue color. You can get these in all kinds of different forms. They do form different kinds of crystals and have different ways of forming. So you can get them from, there's a lot of different mines that are producing them. Some people are concerned about it getting mined out, so it might be getting a little more pricey in the near future, but that's not something that I know a ton about, so good luck if you're trying to get into the rock stock market, essentially. So when I was talking about the lepidolite, the mica, I mentioned that there were some quartz and feldspars around it, all from a granitic source, essentially a granitic magma. This amazonite would be the same thing or similar. It is a type of feldspar specifically, and you can see some other feldspars towards the bottom of it. However, it may not necessarily have been associated with the granitic magma. It would have been associated with a different type of magma. Feldspars are an entire family of minerals, and so that's why this one is so green, why that one is, the one on the lepidolite was very much more white. There's also labradorite, which is blue and shiny and can have some golds in it sometime. Like, there are all kinds of different feldspars. The amazonite is so called because it's much more green, and it's a bit more uncommon, but I really enjoy it. It's a very pretty rock. So rhodochrosite is actually almost the same thing as calcite. So calcite is calcium carbonate, so CaCO3. Rhodochrosite is manganese carbonate, meaning it's MnCO3. So you get a lot of the same kind of properties. You do have a very similar kind of structure on it as far as the crystalline shape, and you also probably want to watch it around acid because you don't want it to dissolve. This is another one that I've been told they might be running out of at some point, so you might want to try and buy sooner rather than later if you are into it. I also just think it's a really nice thing, and I think that carbonate rocks are also just very interesting because it's just cool. Going back to a mineral, I forgot that I actually had this one when I was talking about quartz, but this is Quartz and Epidote. So Epidote is going to be the black parts, the long kind of veiny parts. It's just another mineral that happens to show up with quartz a lot, and then all these little kind of quartz points all throughout. Let me get more of it on the back here too, but not quite as pretty as this area, which would have essentially grown into a vug or something, so it's something where there was more space, so it could show up a little more cleanly. So yeah, this is the final rock. This is a lava bomb that I pulled off of SP Crater in northern Arizona, which if you want to know what SP Crater stands for, you can Google that one, because I'm not going to use that language on my channel. As you can see, this one's very large. You know, baby for size. Yeah, I had to roll this down a hill, and I only ever almost killed one person with it, and had to scream rock at the top of my lungs as it was rolling down there. He got out of the way, so, you know, it's fine. So these are formed when it erupts with a lot of liquid lava flying through the air that cools and hardens in midair before it lands. So it forms this really nice, you know, kind of teardroppy aerodynamic shape. This is a really nice one. A lot of the ones we saw here weren't shaped this regularly. And this rock from this volcano is also interesting because there are little pieces of quartz in it. They're going to be inside of it, but that's something that you don't normally see in this kind of lava. So it's just an interesting thing that it picked up from deep beneath the earth as the lava was coming to the surface. Hi, so we filmed this months ago, and there's been a lot of changes in the United States since then. And I want to say with what's happening in Kenosha, Black Lives Matter, we support those protests and that movement, and the person who showed up there and shot people is a terrible person, and if you support them, I really don't want you supporting me. You know, take care, be safe, wear a mask, don't go extinct.